So, in the last lecture we looked at the data flow or the continuous kind of assignment statement in Verilog and how they can use to model both combinational and sequential circuits. Now, today we shall be looking at the other kind of assignment statement, which is the so called procedural assignment statement, okay? And we shall see the different types and how we can use it in the Verilog language. So, the behavioral style or the procedural assignment statement in Verilog comes in two flavors, and you have already seen some examples using these. These are sometimes called procedural blocks. They come in two different types. One is the initial block, other is the always block. The main difference between these two are the initial block is executed only once, and this is used exclusively for writing test benches or test harnesses, and these are not used in synthesis. When your objective is to synthesize the circuit, you should not use the initial construct. Initial construct is to be used only when you are writing the test benches. It is executed only once at the beginning of the simulation. And the other type is called always block, where this always block can be used inside the test bench, or it can also be used inside your circuit description module. This is like a continuous loop which never terminates. You see, the always block models a hardware circuit in a more natural way. Whenever we design a hardware that is supposed to work as long as power is switched on. Okay? So, we cannot say that this circuit hardware circuit will be working for 10 seconds and then it will automatically stop. It will not stop unless you explicitly send a signal to stop it. Okay? So, the always block is like a piece of hardware which is taking some input, generating some output, and continuously it is doing it in a repetitive fashion. It never stops, it is more like working in a continuous loop. Now, these are called procedural blocks, initial or always. Now, inside the procedural block, you have some code which comprises of a set of sequential statements. Sequential statements means they execute in the order they appear or they are written one by one. Okay? So, let us see. First, the initial block. Well, we have already seen some examples of the initial block, we have seen some test benches, we shall see some more complex test benches later again, but at least whatever we have seen. So, you can appreciate that the statements that appear inside the initial statement, that is referred to as the initial block, and they are typically grouped between begin and end. So, inside an initial block it comes like this. When you give initial, this is a statement. So, inside it the statements are grouped in begin and end, and this is what is defined as a initial block, right. Okay. Now, the rule for execution is that the statements that are there inside this begin end, they start executing at time 0 and they execute only once. This is important. So, if you do not specify any explicit timing by giving that hash command, it is assumed that the first statement inside that block will start executing at time t equal to 0, and initial means the statements will be executing only once. Okay? Fine. And in a typical test bench there can be multiple initial blocks, and if there are multiple initial blocks, then all the blocks will be executing in parallel concurrently and all of them will start at time t equal to 0. This is something you should remember. Now, as I have said repeatedly that this initial block is used to write test benches. But sometimes when you are trying to see how some typical Verilog constructs are working, you can also use initial block just for testing. You can do some computation, you can give a display on a monitor statement to print it just to see whether it is working or not, but not for synthesis. When you are designing and your target is to generate the hardware, you can forget about initial. Initial is something which you should not and cannot use. Okay? Fine. So, this initial block is used for writing the test benches. The test benches, as you have seen, they basically specify the stimulus or the inputs that are to be applied to your design, whatever you have designed, and also it specifies how the output of your design are to be handled, whether they are to be displayed or they are to be dumped into a file, so that you can display the waveforms later. Okay. This test bench specifies all these things and they are typically done inside always blocks. Always means initial blocks. So, some simple example. So, this is the example of a test bench, but I am not instantiating the module because our objective is just to illustrate the initial blocks. Here you see we have used 3 initial blocks, and if there are multiple statements inside an initial block, you need this begin and end, but if there is a single statement, you do not need the begin and end, it is optional. So, all the 3 initial blocks, they start execution at time t equal to 0. You see what is happening at t equal to 0. Okay, this is something like a full adder. You see the names are quite familiar, A, B, carry in, sum and carry out. So, I am initializing with the carry in as 0, and in the other initial block which also starts at time t equal to 0, it encounters a delay of 5. So, it waits for 5 units and then it applies A equal to 1 and B equal to 1. Then it again waits another 5 units and then applies B equal to 0, and that is it. This is a single execution. And the third initial block, this also starts at time t equal to 0, it waits for 25 time units and then calls the system function finish, which means the end of simulation. So, at time t equal to 25, this simulation will stop. So, such multiple means initial blocks are very typical inside a test bench. Now, inside a test bench you can also have always blocks, as we shall see later with some examples. Okay. So, as I have said, to summarize, the 3 initial blocks execute concurrently. The first block, because there are no delays, the statement executes at time t 0. The third block calls finish. So, it terminates simulation at time 25. Okay. Now, just to note that there are some shortcuts in declarations which are supported by Verilog, means at least the recent versions of Verilog which are available now. Now, see, normally whenever you have some parameter in a module which is an output and which is assigned inside a procedural statement which has to be a reg, you declare it like this: output, let us say it is a vector 720 data, and again you have to give reg 720 data to indicate that this data is also a register type, so that it can be assigned inside a procedural block later on in the code. But Verilog now permits us to combine these 2 statements in a single statement like this. You can straight away write output reg 70 data. So, you are specifying 2 things together, that data is an output and also it is a register type variable. Okay. Secondly, see, earlier you used to write something like this, say a clock, you declare a clock as a register type variable, then in initial block you initialize clock to 0. Suppose this is the single statement inside the initial block. Now, this initialization and declaration can be done together in a single statement now. You can write something like this, reg clock equal to 0, because here also you see clock equal to 0 initialization will take place at time t equal to 0, because no delay is specified. Same thing will happen here. Whenever you are declaring clock at time t equal to 0, it is also initialized. Okay? Fine. Now, let us come to the always block, the other kind of procedural block. Now, there is a statement, the always statement, just like we said that there is an initial statement and it comprises as an initial block. In exactly the same way, there is an always statement. Inside the always statement, typically you have begin end again. So, begin end can group several statements together, and this whole thing is called a always block. Right? Okay. So, the set of statements which are behavioral statements inside the always, they constitute the always block, and as I have shown in that example, these block is grouped using begin and end. Now, just like initial, this always block, the statements inside it also starts at time t equal to 0 and executes this statement inside the block repeatedly and never stops. What I mean is that here inside this always block, I have this begin end statement, there can be several statements here. Now, these statements are executed repeatedly in an infinite loop kind of a thing, and it never stops. Initial executes only once, it executes once and stops, but always will never stop, it will execute the block repeatedly in response to some event condition that I will mention very shortly. Okay? This is the difference. So, the always block is typically used to model some activity which is repeated indefinitely in a digital circuit, which is characteristic of a digital circuit. So, as long as power is switched on, it will continue. For example, I have a clock generator. As long as there is power, the clock signal will go up and down indefinitely, it will never stop. So, only when I forcibly switch off the clock generator or switch off the power, only then the clock will stop. Okay? Fine. So, this is the example I have also given here, the clock signal that is generated continuously. Well, for simulation purposes, we can specify delays even within always block, but again when we are actually generating a hardware, the clock generator, this delays doesn't carry any meaning. So, as long as there is the power supply, it will go on. Of course, in simulation you can specify some delay, we can say that after some delay it will stop, but in an actual hardware there are certain things that we cannot do, that we will see later on, because you see you have looked at so many different constructs in the language, something which you can do only for simulation, something you do typically for synthesis. So, we shall see later, we will talk specifically about it. There is a subset of the language which of course is a little subjective, it can vary from one software or synthesis tool to another. There is a subset which is called synthesizable subset. There is a set of statements or set of features which are only allowed by the synthesis tool. If you allow or use any other construct of the language, the synthesis tool will simply ignore them, it will not take them. Okay? Fine. So, here is an example, just a clock generator. So, this is just a module, just like a test bench, which is generating a clock signal. This is an output reg. You see, this initial block at time t equal to 0 is initializing the clock signal to 0. So, initialize to 0 at time 0, and in the test bench I can also give an always block. I have given an always block which says that with a delay of 5, you use clock equal to not clock. What does this mean? Suppose this is my time t equal to 0, and this is my signal clock. My clock was 0 at time t. At time 5, clock equal to not clock, my clock becomes high. At time 10, after gap of another 5, again clock equal to not clock, it will become 0. At time 15, it will again become 1. At time 20, it will again become 0, and so on. So, with a gap of 5, the clock will continually toggle and the time period will be double that delay, it will be 10, 5 off period and 5 on period. So, this is how we specify that after every 5 time the clock will toggle from 0 to 1 and 1 to 0. And just for simulation we can specify this, that at time 500 the simulation should finish. Okay. So, the clock will go on toggling up to time 500. So, inside a Verilog module, initial and always blocks can coexist. You can have a combination of initial and always blocks, but of course, within the test bench only, not within the main Verilog module, and they all execute concurrently. The difference I mentioned, that initial will execute only once, but the always block will execute indefinitely, repeatedly. So, a module in general can contain any number of always blocks. I mean a module where I am describing the hardware, and these blocks are all executing concurrently. Now, I told you just some time back, this always block will be executing in response to some event. You see, this is the general syntax of an always block. After always, you give this @ symbol, and within bracket you give an event expression. So, whenever this event expression occurs or takes place, the statements inside the begin end block will execute sequentially. And this event expression, this is required for modeling both combinational and sequential circuits, as we will see through examples slowly. Okay. So, this is the general syntax. There are a number of sequential statements inside the always block, and every time this block will get executed whenever this event expression triggers. So, let us say this event expression can be a clock. So, every time a clock is coming, it will execute, again next time clock comes, again it will execute, okay? Something like that. Fine, and there are some restrictions here. So, inside the initial or always block, whenever you are assigning some variables to some values, only reg type variables can appear on the left hand side. You can assign values only to reg type variables. The basic reason is that, you see, the sequential always block, as I said, it will execute only when the event expression triggers. Like what I have said is that always @ some event expression, I do not care what it is. What I am saying is that inside the begin end block, let us say I am writing some statement like this, A equal to B plus C, I write D equal to B plus 2, something like this. So, whenever this event expression will appear or will trigger, these two statements will execute. But now think what will happen during the time when this triggering condition is not true. So, what will happen to the statements? Whatever you have assigned to A and D should remain in A and D. That is why we say that the left hand side must naturally be reg type variables, so that if required, these reg type variables can be mapped to hardware registers by the synthesizer. But it is not necessarily true. Sometimes you will see that the variable may be a reg type variable, but whatever you are mapping, whenever you are mapping it, so it is actually mapping to a combinational circuit. So, no registers or storage elements are required, flip flops, latches are not required. So, a reg can map to either a sequential element or a combinational circuit, but if you use a net type variable can never be sequential, it will always be combinational, right. Okay. So, this is what I mentioned, the object which you are assigning must remember the last value assigned. This is not continuously driven. So, you must have reg type variables in the left hand side, but on the right hand side or in the event expression you have any combination of variables reg, var, etc. Now, let us come to the sequential statements in Verilog. So, we have said that inside Verilog or in the always block you can have a number of sequential statements. Such sequential statements can also be there inside the initial block. They are supposed to be executing sequentially one by one. So, what is the idea? There are multiple assignment statements inside a begin end block may be there, which may execute sequentially or concurrently depending upon the type of assignment. This is something we will be discussing later. What you are saying is that inside a begin end block there can be some assignment statements. These assignment statements may execute one by one sequentially or they may be executing concurrently depending on what kind of assignment we are making. This we shall be seeing later. There are two types of assignment statement. One is called blocking, which is denoted by the equal to symbol, and there is another type called non-blocking, which is denoted by less than equal to or the arrow symbol. Okay. Now, the sequential statements, whatever is available in the Verilog language will be explained now one by one. The most important and the basic which I have already seen is the begin end. Begin end is the basic block which combines a number of sequential statements into one composite statement. So, a number of sequential statements can be grouped together. Now, if the number of statement is 1, then the begin end keyword is not required. You can simply write this statement. Right, fine. Now, if else, you see these constructs are very similar to the one which are available in high level languages like C. So, I am showing 3 different types of if else construct. One is a simple if without an else part. If some logical expression, it can be true or false. If it is true, then execute this sequential statement. Now, you see one thing. I have written just sequential statement, and just in the previous one I said begin end is also a sequential statement. So, that sequential statement itself can be this begin end block. So, although I have written a single sequential statement, so there can be begin and end inside if, and there can be 5 statements there. Okay? Several statements can be here inside begin end. So, in the second version there can be an else. If this logical expression is true, then this block or sequential statement will be executed, else this block will be executed. So, you can have a begin end here, you can again have a begin end here. Now, in the third version we are showing nested if then else, if else. It says if expression 1 is true, then you execute this sequential statement, else if expression 2 is true, then execute this, else if this is true, then execute this, otherwise default statement. So, you see the expressions are checked in a particular order. The first match whatever you get, that particular statement will be executing. So, inside this block exactly one of these statements will execute, either this one or this one or this one, and if none of them match, the default one. And here as I said that each sequential statement can be either a single statement on its own or they can be grouped using begin end. Now, we can have a more concise version of this if then, because you see if then else nested one, it becomes quite complex in terms of the structure. So, you can have a concise one. Well, in C language you have a similar construct called switch case. In Verilog we have case. Here you say that we give an arithmetic expression inside this case within bracket. So, it evaluates to a value and that value is compared with these expressions which are specified before the colon. So, it compares with this expression sequentially one by one. It first compares with expression 1, then expression 2, expression 3 up to expression n, and whichever it is matching, that corresponding sequential statement will be executing, and if none of them matches, then there can be a default, then this default statement will be executing, and case will end with end case. So, each of the sequential statements like the earlier ones, they can be either a single statement or it can be a group of statement inside begin else. So, this becomes much more simpler as compared to a complex if else kind of a construct. Now, the order in which you list these expressions, they will actually give you the order in which you are checking, because you see the same expression, the way you are comparing, it can match with more than one condition. There can be some do not care values also. So, the first one that matches will be the one that will be taken. Like there are two variations of case you can have in Verilog. One is called case Z, other is called case X. In case Z statement, here the high impedance or the Z values in the inputs and the expressions are treated as do not cares. But in case X, not only Z, also this X, they are treated as do not cares. Let us take a small example. Suppose I have declared a state vector 4 bit, next state is an integer, I am using a case X on this state 4 bit, and you see the values of the expressions I am specifying, they have do not cares, they are not crisp values. I am saying 1 do not care, do not care, do not care, x 1 x x, x x 1 x, and here last one is 1. So, depending on which one, here I am saying that if the first bit is 1, then next state is 0, you do this. If the second bit is 1, you do this. But if none of this matches, that means none of the bits are 1, then default something you can say, here I am saying next state 0. You see, if your state has a value, let us say 1 0 x x, this will match with the first condition which is 1 x x x, because 0 and x matches, x is do not care and 0 is one possible value of the do not care. Okay? But if you give only case, then these will not match, but if you give case x, then only the first bit is in state is 1 or not, other 3 can be anything. Okay? Need not be x x x, need be 0 1 x, 0 1 z, anything. Okay? So, this is how you can give. So, there are several other kind of this kind of constructs also. So, we have only seen a few, begin end, if then else, case. So, in our, this is what I am saying, if the state is this, say as an example 0 1 z x, this second expression will be matching 0 1 z x, because x matches with anything, okay, and next state will be 1. So, so in the next lecture we shall be continuing with this. We will see that in Verilog there are some other kind of sequential statements also available, because we have so far talked about begin end, if then else, if else, nested if else, and case and some versions of case. We have not talked about the different looping constructs for, while, and some others. So, in the next lecture we shall be talking about those, and also we shall be seeing some examples. Thank you.